Okay, so this is the first example that we have for finding the simple derivatives of parametrically defined functions. So we x equals 5t squared and y equals 10 natural log t. And we're going to find the first derivative and the second derivative. And there's supposed to be a 2. So there's supposed to be a subscript 2 right there. I did not notice that the first time I wrote this out. Sorry. But, so that's supposed to be there. Okay, but we can now proceed and take the first derivative, right? So, this is not incredibly difficult, right? We've just, so remember what we said, dy dx is dy dt over dx dt is what we said. So what does that mean for us? Well, we're just taking a regular derivative twice, and then you're doing a quotient. So, okay, this is not that bad. So this is y equals 10 natural log, different color. Y equals 10 natural log of t, right? So we want to find dy dt, so the derivative of that, okay, right? That's 10 over t, we know that. That's simple, right? Okay. Can't get that t right. But, so then we have x also here. So we want to find the derivative of x with respect to t, right? So that's simple. That's just 10t. Okay, so here we are. I mean, this is it. This is our answer, just with a little more simplification. So this would be 10 over, not 10. The 10's cancel out, so we just have 1 over t squared. So this is it. This is our dy dx. This is our dy dx, our derivative. Okay, so there you go. Now find our derivative also in terms of, or we can find the second derivative now, which we should do. So, so remember that the second derivative is the derivative of dy dt with respect to t over the derivative of x with respect to t. So we already got this far, right? With 10 over t over 10t, right? So we can kind of like plug that in here. So what that means is we're going to have 10 over t, 10t. What we're saying, though, is that we have to, there's the dt there. So we have to put that there and take the derivative of the numerator with respect to t. So this is what our second derivative is going to be. This is, once again, not that difficult. So our second derivative, so if you want me to write this out, I can, right? This is 10t to the negative 1, technically, right? So it's just simple power rule, but you guys know this. You guys are second-year calculus students. So negative 10t to the negative 2 power over our 10t. So nice, right? Simply t to the negative 3. Okay, so this is our second derivative function. Oh, wait a minute. This is weird. Look at these two. They're related. If I were to take the derivative of this, if I were to take the derivative of 1 over t squared, I would get t to the negative 3. With a negative sign, actually. I left out the negative sign here. But now that the negative sign is there, my point is actually correct. My point actually makes sense. If I were to take the derivative of 1 over t squared, I would get this right here, negative t to the negative 3 power. What? Why is that true? Oh yeah, this is true because this is the first derivative and this is the second derivative. This is the first derivative and this is the second derivative. So of course taking the derivative of this will give me this. So then you're probably like, why did I just go through all this mess right here? to get the second derivative when I could have just done the power rule here and gotten this answer, right? I'm sure that's what you're thinking. And the reason why I did it was to show you how to find a second derivative. But yeah, of course, we could have done that. We could have taken the shortcut. It would have been easier. But I didn't do that. So yeah. But and as I said in the intro video, I mean, now you get to see it evidently. It's evident that these derivative functions are in terms of t. So, in the instance, in a situation where you might be asked to find a derivative function in terms of x, actually. So they give you a parametric function still, but they ask you to find the derivative in terms of x, not in terms of t. So this would not be an acceptable answer because there's t in there. If they did ask you for that, as I said in the intro video, what you would do is you would have to convert your parametrically defined functions here into regular non-parametrically defined functions, and then just take the derivative like you would normally take the derivative. And so, like, what that would look like is, so, like, I mean, this is a little bit of a mess. T equals x over 5, the square root of x over 5, right? Solving for t in the first equation, and then you can plug that into this equation. So you have y equals 10 natural log of square root of x over 5. That's slightly problematic in a way. Slightly a bit annoying. But this is what your non-parametrically defined function would look like, the equivalent, basically. I mean, you have to be just as a warning, disclaimer. You do have to be very cautious of, like, different, like, implicit domain restrictions and stuff that might be on your new non-parametrically defined function, and so it might not be exactly equivalent to the two parametrically components combined together. It might not be exactly the same. Like, for example, here there is a square root, which means you can't get negative numbers out of there because it's a principal square root. Although there's a negative, although there's a natural log actually, so you couldn't take the natural log of a negative number anyway. So actually, it doesn't matter here. But that is a disclaimer, just in general, for if you ever convert parametrically defined functions into regular functions. But so then to find the derivative function that is in terms of x, now all we have to do is take the derivative of this. Take the derivative of that with respect to x, and you get it. And that actually wouldn't be that difficult. It's not that much of a mess when it comes to taking the derivative. It's just applying the chain rule once. You apply the chain rule once. So it's not that big of a mess. And so that would get you your derivative function in terms of x. If you're not asked to find the derivative function specifically in terms of x, then these might, would work fine, I guess. And this is normally what you'll be asked to do. You'll be asked to find your derivative function in terms of t. Anyway, so that's the first example problem for the parametrically defined function simple differentiation.